Hello everyone and welcome back again to another video. This is part 2 out of 2 of limits. So last video we just went over some basic rules. In this video we'll be continuing further by looking at L'Hopital's rule as well as the trigonometric limit. So if you're already familiar with these, feel free to skip ahead to the practice problems that come afterwards. But we'll start with a brief introduction to the to L'Hopital's rule and to the trigonometric limit. So L'Hopital's rule states that the limit as x tends to some constant c of a function f of x over another function g of x equals the limit as x tends to c of the ratio of their derivatives. So that would be f dashed of x over g dashed of x. And there are some restrictions given over here that we will be going over. So we haven't covered derivatives yet on this channel, but we will do so in the future. So this, of course, is only applicable if you've seen derivatives. So the restrictions say that obviously g dashed of x cannot be 0 because we have the g dashed of x in the denominator here, and we can't have 0 in the denominator. So this restriction is pretty self-explanatory. And then as for the other one, we have this one and we have this one. They don't both have to be true, we just need at least one of them to be true, okay? So the first option would be that both f of x and g of x tend to 0 as x tends to c. So that would give you in quotation marks the form 0 over 0. And the second option would be that you have infinity on the denominator or negative infinity for g of x. So that would be something over infinity. I'm writing k here, but it can be anything, or over negative infinity. So those are the restrictions. So you can apply L'Hopital's rule, for example, when you get 0 over 0, or when you get, for example, infinity over infinity. Those are the most common cases in which you would use L'Hopital's rule. Now, as for the trigonometric limit, it's just a specific limit, the limit as some angle phi tends to 0 of sine of that angle phi over phi. And we know that this is equal to 1. And although it's specific, it's actually quite useful because we can often rearrange limits to get them in this form and just say that that part is equal to 1. Okay, let's try to apply this with some exercises. So we have the limit as x tends to 0 of x squared over x. Here we can just use exponent laws to simplify this simply to the limit as x tends to 0 of x, and that is just 0 by direct substitution. We can do direct substitution originally because we would have 0 in the denominator. Okay, next we have the limit as x tends to infinity of this rectangular hyperbola. So this is a great exercise for applying L'Hopital's rule because both functions are really easy to differentiate. And of course, we will be getting infinity over infinity in quotation marks if we were to just apply direct substitution. So we are allowed to use L'Hopital's rule. In this case, we have two linear functions, so the derivatives are just the coefficients of the term would be x, so that would be 2 over 7, and that's our final answer. Okay, the next limit we have is the limit as x tends to 0 of another rectangular hyperbola. Now, let's try first direct substitution and see what we get. So we'd have 3 times 0, which is just 0 plus 1, over 3 times 0, which is just 0 minus 1. And that's just minus 1. So that's our final answer. We can't just use L'Hopital's rule because we don't have a form of 0 over 0 or infinity over infinity, and that's required. So we have to just use direct substitution. Okay, so for this next one, if we were to just do direct substitution, we get minus 1 over 0. And yes, we have a 0 in the denominator, but we have a minus 1 in the numerator, so we can't use L'Hopital's rule. And instead, we just say that this limit doesn't exist, because it approaches infinity from one side and negative infinity from the other side. And you would know that by sketching it, but it's also useful to remember as a rule that whenever in quotation marks you get some constant over 0, where the constant is not 0, then this is just undefined, does not exist. If the constant is 0, we would actually have 0 over 0, and then we can use L'Hopital's rule or some other technique. But if at some point we ever get to a non-zero constant over 0, we can just say the limit doesn't exist. Okay, now we have the limit as x tends to 0 of x over sine of x. So we notice that this is really close to the trigonometric limit, except that the trigonometric limit has sine of x over x, and here we have the reciprocal. So how can we deal with that? Well, we can say that this is equal to 1 over the inverse, sine of x over x. Okay, this expression is the same as this one, and actually we should also still have our limit, of course. And now we can use limit laws from the previous video to split the limit, transfer this up here and down here. Okay, so this would be actually the same as the limit as x tends to 0 of 1 over the limit as x tends to 0 of sine x over x. Okay, now we know that this limit is just equal to 1, right? The denominator is just 1. That's just the trigonometric limit. And the numerator, well, we have a constant for a function, so it's independent of the limit. So we know that this is just the constant, which is 1. So we have 1 over 1, meaning that the final answer is just 1. Okay. The limit as x tends to 0 of the sine of 2x over the sine of x. So for limits like these involving sines and cosines and so on, it's good to know your trigonometric identities. And in this case, it helps to rewrite this as the limit as x tends to 0 of 2 sine of x cosine of x all over the sine of x. And this comes from the fact that the sine of 2x is the same as 2 times the sine of x times the cosine of x. This is just a trigonometric identity that you should know by heart. So here we notice that we can just simplify by the sine of x. And we're left with 2 times the cosine of x. If we let x tend to 0, we can just do direct substitution. The cosine of 0 is 1. So this term is just equal to 1. And we're still multiplying by 2. So this whole thing is equal to 2. Okay, so we have the limit as x tends to 0 of the cotangent of x. Let's just rewrite this as the limit as x tends to 0 of cosine of x over the sine of x. Whenever you have a tangent or cotangent, it could always be useful to just rewrite it as either sine of x over cosine of x or cosine of x over sine of x. So, and in this case, when we do direct substitution, we get cosine of 0 being 1 over 0, because sine of 0 is 0. And again, we have this constant over 0, in quotation marks. And we know that this limit doesn't exist. So we just write DME. And the reason for that is that if you were to sketch it on a graph, it approaches infinity from one side and negative infinity from the other. So the graph would look something like this, 0 being here. So from the positive side, it's going to positive infinity, and from the negative side, it's going to negative infinity. Okay, let's do the next one. We have the limit as x tends to infinity of x over the natural logarithm of x. So as always, let's first try direct substitution. We get infinity over ln of infinity, which would still be infinity. All right, so we can apply L'Hopital's rule, since we have the form infinity over infinity. Now the derivative of x is just 1, and the derivative of the ln of x is 1 over x. And now this whole expression should, of course, be after a limit. And this is just equal to the limit as x tends to infinity of, well, x, right? This is just equal to x. And, of course, that's just positive infinity. Okay. We have the limit as x tends to infinity of x cubed minus x over 5x squared plus x. So before doing anything, we can immediately just simplify by an x, because we have an x in every single term. So let's rewrite this as the limit as x tends to infinity of x squared minus 1 over 5x plus 1. Okay, now direct substitution gives us infinity on the numerator and infinity on the denominator. So let's apply L'Hopital's rule. Differentiating the numerator is going to give us 2x, and differentiating the denominator gives us 5. And now we have 2 times infinity by direct substitution, which is just infinity over 5, and that is just infinity. Infinity divided by any constant, or infinity times any constant, is always just equal to infinity, given that the constant is not 0, and in this case it's 5. So we know that this is just infinity. But if you wanted to be sure, you could just apply okay. So next we have the limit as x tends to infinity of e to the x times x to the power of negative 1. So by direct substitution, we would get e to the power of infinity times infinity to the power of negative 1. Okay, now infinity to the power of negative 1 is 1 over infinity, which is 0. So this and e to the infinity is just infinity. So this is infinity times 0, which is an indeterminate form. So how do we deal with that? Well, we have to turn it into a fraction, a division, where we can actually apply L'Hopital's rule. And the way to do that is to rewrite this as the limit as x tends to infinity of e to the x over x. And these expressions are indeed the same by exponent laws. And now if we were to plug in through direct substitution the x tending to infinity, we would just get infinity over infinity as we want to. And we can easily just apply L'Hopital's rule from here. So differentiating the numerator and the denominator gives us the limit as x tends to infinity, okay, of e to the x over 1. Now we can just do direct substitution. We get e to the infinity over 1. E to the infinity is just infinity. And dividing by 1 doesn't change anything, so this is just infinity. Okay, let's move on to the next one. We have the limit as x tends to infinity of e to the x over x to the power of 50 factorial. If you haven't seen the factorial yet, it's not that important. It just means we have a power of x that's very, very big, but constant and independent of x. So just a very big number, but it is still a constant. It doesn't depend on x. So obviously, we have infinity over infinity, right? So we can apply L'Hopital's rule. Now let's imagine applying L'Hopital's rule multiple times. No matter how many times we apply it, we're always going to have e to the x on the numerator. Now on the denominator, what would we have after applying L'Hopital's rule a bunch of times? Well, let's think of x to the power of 50 factorial as just x to the power of k, where k is a constant. Specifically in our case, k would be 50 factorial. Now after the first time applying L'Hopital's rule, when we differentiate this, it's going to be k times x to the power of k minus 1, which is just the power rule. And differentiating again will give us k times k minus 1 times x to the power of k minus 2. And you can notice a pattern. After sufficiently many applications of L'Hopital's rule, we're just going to get a new constant, k2 times x to the power of 0, right? Because the exponent, the power keeps on decreasing. So after sufficiently many differentiations, we're going to reach x to the power of 0, which is just 1, okay? This is equal to 1. So we have this big, big constant, k2 times 1, but that's still just a constant, right? So I'm going to say that this is equal to the limit as x tends to infinity of e to the x over a constant k. And it doesn't matter that this constant is very big, because we said that, well, e to the power of infinity is just infinity, okay? And so we have infinity on the numerator, and if we were to divide infinity by any constant, no matter how big, it's still just going to be infinity. So that's the value of our limit. And this is the last example. We have the limit as x tends to infinity of pi to the x over e to the x. And the best thing to do here is just we have a limit as x tends to infinity. The best thing to do here is to just use exponent laws and have this exponent outside of the ratio. So the way we would do that is like this. Okay, these two expressions are equal by exponent laws. Now, let's look at what's inside the brackets. We have pi over e. If this thing is equal to 1, and we raised 1 to a very big power, then we would just have 1 as our answer, right? But if pi over e was less than 1, and we raised it to a very big power, then we would have 0 as the answer to our limit. But if pi over e is more than 1, then our limit would be equal to infinity, because raising a number more than 1, such as 2, to a very high power like infinity, that would just give us infinity. So we have to just determine which of these cases we're in. Is pi over e equal to 1, less than 1, or more than 1? And since pi is more than e, then pi over e is more than 1. So this limit tends to infinity. And that's it for today's video. Thank you everyone for listening, and I hope to see you in the next one. The next video that I personally will be doing, now that we've covered limits, will probably be the next step in calculus, introduction to differentiation, and then we'll look at the different rules for differentiation, and then we'll slowly move on to integral calculus.